Today on the show, we're diving into three very different frontiers of AI infrastructure and optimization. First, UC Davis introduces CXL Cluster Sim, a new way to model disaggregated memory for large-scale systems. Then we'll explore GPU forecasters, where language models from the world of OpenAI, Google DeepMind, and DeepSeek-style systems become selective surrogates for kernel tuning. And finally, Amazon Web Services takes us inside RNG, a production flat data center network built at scale. Let's explore the first paper, CXL Cluster Sim Modeling. CXL-based disaggregated memory cluster for pooling and sharing using Gem 5 and SST. Kaustav Goswami, Mariam Babai, Hoa Nguyen, Venkatesh Akella, and Jason Low Power at the University of California. Davis present CXL Cluster Sim, a full system simulation framework for CXL-based disaggregated memory that combines Gem 5's high-fidelity OS visible execution with SST's MPI- parallel scaling. The novelty is a two-phase workflow. Gem 5 fast-forwards each host through Linux boot and application initialization, checkpoints the region of interest, then SST restores synchronized, timing-accurate execution across multiple hosts and a remote memory blade. The framework models both CXL-style memory pooling, exposed as NUMA nodes, and memory sharing, exposed as DAX, DEV, DAX mappings for direct byte addressable access. Validation shows the simulated remote link reports stream bandwidth within 0.99% of baseline measurements, and SST's memory controller statistics are within 0.1%. In an 8-host stream study, pinning data to the remote pool reduced effective bandwidth to 6.45 gigs S per node under interleaving versus 11.4 gigs S for local memory, while adding 170 ns and 250 ns CXL latency reduced bandwidth by 8.95% and 29% respectively. For pooling, NAS parallel benchmarks class D showed that larger remote fractions sharply reduce IPC, with MG falling to 0.38 relative IPC when 52% of its 27 GIB working set spilled remote. For sharing, GAPBS kernels on a single shared graph achieved 31.8% of memory instructions from the remote blade, but pointer-chasing kernels suffered the largest slowdowns. The authors position CXL Cluster Sim as an open-source platform for exploring hardware, software co-design beyond NUMA emulation, and note future work on hot plugging, coherence, and switch modeling. Let's explore the second paper, GPU Forecasters Language Models as Selective Surrogates for Kernel Runtime Optimization. GPU Forecasters introduces a new role for large language models from OpenAI, Google DeepMind, and DeepSeek-style frontier systems. Not just kernel generators, but selective surrogates that predict GPU kernel speedups and know when to abstain. The authors from UNC Chapel Hill, AI2, Johns Hopkins, and UT Austin recast kernel evaluation as an 8-bin relative speedup forecasting task over Triton and CUDA code using NVIDIA A100 measurements as ground truth. On a held-out set of 480 Triton kernels across 6 GPU mode workloads, off-the-shelf models already recovered 79.9% to 93.1% of available speedup, under 1%, 50% measurement budgets, with Gemini, 3 flash best on ranking but poorly calibrated, and GPT OSS 2.0b stronger after training. They then fine-tuned OpenAI's GPT OSS 2.0b with reinforcement learning using correctness plus calibration rewards and found that a briar-shaped objective improved both confidence, reliability, and search utility. Speedup recovered rose by 2.06 percentage points over the untrained baseline, while calibration error fell by 0.106. In end-to-end PUCT search, the surrogate let the optimizer evaluate 4 times as many candidates per GPU budget and found faster kernels than the equal budget baseline on 4 of 6 tasks. The paper's broader claim is that calibrated LLMs can act as virtual GPU models, using uncertain forecasts to defer only hard cases to expensive hardware measurement. Let's explore the third paper, RNG Flat Data Center Networks at Scale. RNG, Flat Data Center Networks at Scale, from Amazon Web Services, presents the first production deployment of a flat, expander-based data center fabric built from quasi-random graphs. The paper solves 3 long-standing blockers for expander topologies: scalable routing, practical cabling, and predictable design. Its Spraypoint protocol is a fully distributed demand-oblivious routing scheme that uses ECMP plus controlled waypoint spraying to create close to the maximum number of edge disjoint paths. In evaluation, it finds over 50 edge disjoint paths for almost all endpoint pairs, and over 60 for half of them in a 6-4 degree fabric, versus a median of 5 for 8, shortest path routing, and 35 for 6-4, shortest path routing. For physical deployment, RNG introduces Shufflebox, a passive optical device that internally shuffles fiber connections, so cabling complexity stays comparable to fat trees while preserving expander connectivity. The authors also derive analytic models for path length, oversubscription, and cost, showing that RNG can be 945% cheaper than equivalent fat trees and, at the same oversubscription ratio, often delivers higher throughput across click, hub, and matching traffic patterns. In production benchmarks on Amazon's server mesh and edge mesh, RNG matches fat tree performance for multipath transport and storage workloads, despite variable path lengths. The key novelty is that Amazon is not just proposing an expander network. It has made one operational at scale and defaulted it for most workloads. That's a wrap on today's AI paper highlights. Thanks for watching.